starting up a new recording. And okay, so go ahead. What was your question?
Yeah, so I was just wondering if the pits if you know if the pits happened fairly close after the lava flow happened, or over longer periods, which is what I would assume, but I don't know.
Yeah, well, that's a good question. I'll go back to it.
I mean, I would guess they would degrade.
Yeah.
Time.
So we do see a lot of collapsed rill features. So like sinuous looking, they almost look like river channels, but they're actually some collapsed features because they'll have like chains of pits in them. And so clearly the lava tubes that are there have been collapsing over time. So there is evidence that that's an ongoing process. For the pits, these pits here, the skylights, I'm not entirely sure how old they are. It's hard to date them because they're constantly collecting new material in the floor, so it's hard to date them by craters, and there's just not really enough area there to do that anyway. So one of the things that people have proposed is a mission actually to go into these pits and collect some of the floor material. They think that under the overhangs, in particular in the caves, where things have been protected from the solar wind, they may be able to collect ancient regolith that's been unmodified for however long it's been down there. So that might actually be able to help with the collapse occurred. Yeah, but that's a really good question.
And then also, what's the difference between the red and blue lavas?
Oh, right, yeah. So the blue generally reflects titanium. So there's a lot of features on the moon that have kind of a bluish hue to them. Ina is actually another one that has a little bit of a bluish hint to it. And I think that's largely due to the fact that there's a high titanium content in the lava. And so when, it's particularly in Ina, where it seems to have fresh exposures, it's even more blue looking than the Mare itself.
And then I also wanted to ask about the elliptical orbit, where it's coming closer to one pole than the other. Is there reasoning behind that?
Yeah, we wanted to save fuel so we could be there longer.
And so did you have to make a choice of, well, which is the one which is the pole we want to get closer to?
It turned out that being closer to the South Pole was dynamically more stable and required less fuel. At least that's my understanding. I'm not an orbital dynamicist or anything. But that's what I remember the discussion being about. The other thing is that there's a lot of people interested in the South Pole because there's a possibility of getting at the polar volatiles there, so the water deposits. And there seems to be a better distribution of those at the poles, and so a lot of people are interested in going there and seeing if they can measure the different types of volatiles in water, determine its content. And so being closer to the South Pole provides better data for many of the instruments.
Thank you.
Okay. I actually thank you so much, Julie. This was really, thanks for taking the time to do this.
Yeah.
And I have, this one I was actually taking some notes, and all kinds of questions came up. So I have some of my own. Well, first of all, I interrupted you about that graphic with the visualizations of the moon and different types of data. And that, like I was saying, that would be, I can picture that as as a free full dome image for any planetarium to use about this, about that mission. But could you provide? I mean, could we make a visualization like that? Or, I mean, in other words, would you provide us with the basic picture? And if we change the text, would that be?
I think it's out on the internet. So yeah, I can probably send it to you.
Because that had infrared, ultraviolet sunlight, radar, elevation, and one other. I think there were 6.
Yeah, there was the neutron detector.
Oh, neutron.
And there's one other thing in there too. Oh, the far UV, so alignment alpha.
So another question that came to my mind when you were showing the different types of eruptions. Actually, there were 2 things that came to my mind. One is a natural question that an audience member would ask is how high, what's the relative, comparing the heights of the eruptions, how high the material might go on the moon versus the Earth, and also the different types on the moon. The pyroclastic cones versus the volcanic Hawaiian, I think it was.
Yeah, so those are just general terms for different styles of eruption, but it's basically the Vulcanian, Hawaiian, Strombolian. They're all type classic examples of terrestrial volcanism, so they've been applied to the moon. But in the lunar case, what happens is because of the lower gravity and the lack of an atmosphere, you do get a little bit different behavior of the distribution of the materials that are erupted. So for one, the lava generally is erupting hotter, and it's very low viscosity because its composition is different, a little bit different than typical terrestrial basalt. And it also is coming from very deep within the moon's crust, so at the crust mantle boundary. And so when it erupts, it has to erupt with a lot of force. And so it's rising very fast, it's hot, and it's low viscosity. So it comes out and just spreads out like crazy. So that's why the Mare plains are so vast. It's kind of like the example of flood basalts that you get in Washington State. But when you start building the volcanoes, on the moon, they tend to be shorter, like less tall in relative terms. So compared to the diameter, the height is lower. The flanks of the features are also usually shallower, and the reason for that is probably because the materials are spreading out more widely due to the lower gravity as well as the lack of atmosphere. So they just don't build up a really steep cone in most cases. The one exception to that are the cinder cones, which are very comparable to terrestrial cinder cones, although one of the things I did was actually measure them. So I measured their heights and their diameters and the sizes of their summit craters. And it turns out they are actually, in relative terms, also shallower than terrestrial examples. You don't actually see it by eye, but when you measure it, they are. And so that is one way in which the lunar volcanism differs. The other thing is the lack of atmosphere. So when you get the pyroclastics, there's no wind to slow it down. So in Hawaii, for example, when those cinder cones erupt, there's usually a prevailing wind pattern which pushes the pyroclastics in one direction preferentially. So you'll get these very asymmetric cones where all the pyroclastics are stacked up on one side. Kind of looks like a horseshoe, if you want to think of it that way. And on the moon, it's really weird because you still get this horseshoe shape. The difference is that it's because the lunar cones are forming on a sloping terrain, and so all the material tends to preferentially accumulate on one side, and then eventually it forms a lava flow and it flows away, taking away the material that was on the downslope side. So you still know what a horseshoe-shaped cone, but by a totally different means. And then you asked a question about like the height of the pyroclastics. So the thing about very explosive eruptions on the Earth that have all this gas and it shoots out. So it shoots up into the atmosphere very high, and then the atmosphere it basically gets transported along with the atmosphere, and so its distribution depends on the atmospheric behavior. Whereas on the moon, everything is holistically dispersed. So it comes out, it has a ballistic pattern in the vacuum. It's expanding very rapidly initially because you're going from a pressure to zero pressure. And so it still expands very rapidly, it's just holistically in place. And I'm not entirely sure exactly what the difference in heights is. That is a good question, which I don't know.
Well, now that I think about it, there are so many, there's like what you just said is a whole bunch of, variables that, like for instance, on the Earth, the eruptions may be actually more powerful. How much energy actually is there in the eruption? Then, I guess that's a different, it gives rise to new questions is the Earth eruptions more powerful than lunar eruptions? And that would affect how high it would go. So, and the atmosphere, as you said. But I want to make a comment actually, which may turn into a question. This is a different question, unless somebody else has a question in the meantime. I thought of, I have an interest in audience participation activities in the planetarium. There's a whole community of planetarium people who do that with live programs and, having questions for the audience and activities for them. And one that came to mind was that diagram you showed of the different types of volcanic activity, or I don't know or igneous. Some of it was igneous activity, maybe. I don't know if it's called volcanic in every case, but
this one?
Yeah, that one. It seems like after you showed that picture, there were examples that were given. I think that's what I was seeing, was there were some examples that were illustrative of some of these, if not all of them.
Yeah, all of them. I didn't show the four fractured crater.
Yeah.
The image at the end of the presentation, very last slide, that does have a four fractured crater. We can go check that out right now if you want.
But anyway, the idea for the activity was to show those, show an audience those different types, and then with those words still up on the dome, show the different images and see if they can, would it be possible for people to associate or guess, which image was associated with which type of volcanic activity.
Yeah.
That I thought might be neat activity. With that type of program, this is something I've pointed out for I mentioned the Data to Dome initiative, how to visualize scientific data on our domes. And some of it is just related to just normal flat screen visualization, which you showed examples of. But I've always argued that a critical element of that is to be able to have a narrative or a story that goes with the image. A lot of times the images is shown with an incomplete or inadequate or lame story to go along with it, where when you give a talk like this, you make the image come alive with certain descriptions and certain words that we really need to make it would come alive for the audience too if we used similar kinds of words and so that's something I'm always looking for, is narratives to go with images, which is one reason why we're doing this.
Yeah. Yeah, it's always interesting to see how different audiences react to certain images too. Like sometimes it's like the thing that you don't find as scientifically interesting that the audience really latches onto, and they're like, oh wow, that's really exciting. I've never seen that before. But maybe it's not like gonna answer any great unanswered questions in your science, but still exciting for somebody to look at. So
Yeah. You know, with the image you showed of the mounds, the IMPs or the imps,
yeah,
not to be confused with wimps. Uh, the irregular mare patches. You said those were smooth mounds and the first or deposits. And when I was looking at the first picture you showed of that, I was thinking that's not a mound. That's a hole in the ground.
yeah.
This is this is a
every-
really neat thing to deal with audiences. Which way is the sunlight coming from?
Yeah, almost everyone sees those backwards at first. It's amazing.
Yeah. I think it's because it looks like it's upside down. I mean, to imagine it as a mound, you have to look like it's upside down in that particular picture.
For me, even sometimes like rotating it doesn't help. It still looks like it. Yeah.
But on a later image, this is interesting. On a later image, you showed something with little craters on it too. And it occurred to me that looking at a picture of a crater, once somebody is a novice and, you know, somebody who is a novice and just barely becoming familiar with it, to recognize which way the sunlight's coming on a crater is a dead giveaway, you know, because you know what a crater is supposed to look like. And
Yeah.
and so that helps when there's a crater in the image.
I didn't remember to stop and point out the different craters, but that is an excellent thing to do.
I think that's a whole other activity we can do in the planetarium, is which way is the sunlight coming from?
Yeah,
That's a good classroom activity too.
For example, you know, a mound with a crater right in it. And so
Yeah, exactly. Is this a mound or is this a hole in the ground? A depression. Let's see. Other questions?
Yeah, I've got more. I'm wondering, well, here, I'll try starting my video so you can see me. I was just wondering if there's any indication of any change in the types of lava flows over time. So were the more recent ones, were there more, yeah, I guess were more of a different kind of lava flow recently than in the past? I realize the ones in the past have been covered up to some degree, but is there anything you can say about that?
You know, that's a kind of an ongoing study. It looks like there might be a trend in titanium over time, with the later flows becoming returning titanium. But that's still kind of up for further research. The thing about the flows is that they tend to vary by basin. So, for example, Imbrium and Serenitatis and Tranquillitatis and all the others seem to have their own individual flavors. And so the sequence of eruptions in each basin seems like it's different from basin to basin. So it seems like it's reflecting a local progression or evolution of the magma beneath it.
Mm-hmm.
But yeah, that's something that people are very interested in. Because one of the other questions we have in lunar science is, so there's this area that's enriched in radioactive elements on the lunar side, particularly centered in the Planetarium region. And so one of the questions we have in lunar science is, why does volcanism last longer there? And I think it's related to the fact that there is a greater concentration of these radioactive elements there, like calcium and thorium. But this also results in the possibility of there being other late stage and incompatible element enrichments, so other things that tend to hang around in the mantle longer. So as all the early eruptions occur, we depleted in those elements, and then later ones They basically have to take up whatever's left in the mantle. So that's one other thing that we're looking for is how that story fits into the stratigraphy of the Maria over time.
And then what about the far side? I know, it's basically highlands, but is there any indication of much activity over there?
Yeah, so most of it is concentrated in the South Pole Aiken Basin, which is the lower third of the far side. And there's also little pockets of volcanism here and there. It's kind of scattered around, and people are trying to figure out if this is a case of where there's cryptomaria, so that's basically ancient volcanism that's been buried by younger deposits. So one of the possibilities is that there was volcanism there, but it's been buried by later ejecta from the different basins that had deposited their materials on the far side. So overall, though, there's no great concentration like on the near side where you have the Coquitlam terrain and the Imbrium Basin. Don't have that same concentration.
And then is there any information you can get from studying like the ejecta from craters?
Yeah, so that is one way you can find these buried Mari deposits is to look at crater ejecta. So often in the highlands, you'll find a crater with this dark ring of material around it, and that's the dark materials in its ejecta. So if you had a buried Mari layer, it's rich in iron, so it's bulk compared to the highlands. And so if that gets excavated by a crater, you'll end up with dark material in the ejecta, but the rest of the crater and surroundings is bright. And so we use those to map out potentially buried Mari deposits. And that's one way we do find some of those more ancient Mari flows.
And then, so the moon's close, interesting. I'm kind of playing devil's advocate here, but can you go into what's useful about this study?
Oh, okay. So
besides, more knowledge is power and all that, but yeah, any Earth side applications and that sort of thing?
Yeah. So from my perspective, the moon is useful because it is basically a laboratory for many of the processes that happen on Earth and the rest of the solar system. So there, for example, impact craters are ubiquitous throughout the solar system. We have some remnants of them on the Earth, but they're not very well preserved. The problem with Earth is that everything gets degraded really quickly thanks to our water and wind and people sometimes. And so over time, impact craters and other landforms degrade and break down. And so it becomes hard to see them in their pristine state. Whereas on the moon, even really old processes that happened billions of years ago are still really well preserved today. So we could go there even from orbit. We can learn a lot about the processes that have affected Earth over time just by looking at the images and checking down there and collecting samples. And the other thing about it is that it is interesting because we have, it is so close nearby that we have the potential to go back there someday, and it's much easier to get there than it is to, say, Mars or somewhere else in the solar system. And so it does give us a chance to test out ways that we can use, say, pyroclastic materials, which contain a lot of fundamental building materials, oxygen and water and iron and metals and trace elements that potentially could be used to manufacture things on the moon someday, or test things for an eventual trip to Mars and that sort of that sort of interest.
So is there like one place you'd just love to go to on the moon to study some things up close and in person after, just studying images?
Yeah, well, I think one of the biggest unanswered questions are what are the IMPs? They just don't make any sense. From what we know about how planets cool, it doesn't make any sense for them to be as young as they look. But they also, how could they possibly have survived 3.5 billion years in their current state? Just neither answer is particularly satisfying. And so I think we should go there and get a piece of one and see what it is. Even just getting a robot on the surface, I think, would give us a much better insight into what they are. My other favorite place is the Marias Hills, though, just because I'm particularly keen on those cinder cones. I think they're really neat, but they probably don't have such a significant impact on our understanding of lunar science as it would to know whether or not the moon was still volcanically active 100 million years ago.
So, yeah, go to the IMPs for science and go to the cinder cones for vacation.
Yeah, exactly.
Actually, I'd like to go into one of those pits.
Yeah, I like those. Yeah, those are pretty intriguing.
Yeah, there's so the Japanese space exploration, NASA's equivalent JAX over there. I forget what the acronym stands for right now, but they are really keen on putting habitat inside one of those pits. And they come to conferences and they have these wonderful pictures of, their glass dome in there, and it looks really cool. So I hope they make that a tourist destination soon.
Great.
Yeah, I have one more question if we have time for it. And I guess, and it has to do with it's a clarification, actually. It has to do with how old, that question about how long ago was the last volcanic eruption, or how long ago did eruptions occur. Actually, this is in two parts. The first part is you used a unit, like the last Mare eruption was 1.2 GA to 900 MA. And those units, I assume, are like billions of years ago, or millions of
and million and I don't know what M is. Megan, something like that. Million though.
a giga. It would be a giga A. But I mean, what is the unit? What if you had to say that unit? What would you say?
Giga-N is what I would say.
Well, could we say
stands for billion years ago?
Billion years ago. Okay, so that's a giga annuums. And just a comment, actually, that 1.2 to 900, 1.2 GA to 900 MA is a very scientific way of stating an error bar.
Yeah.
That's an error bar. And for the general public, we might want to just say, well, would we be safe in saying that's about 1 billion years ago?
Yeah. Yeah.
No. But then the question, the deeper question associated with that is, how was that determined? Okay, how did those things get determined?
Yeah, so I kind of hinted at that a little bit. We basically look at all the superposed impact craters across a single Mare flow. So we map out a flow, one that we think is compositionally distinct and uniform. And then we draw an outline around it, basically. And then we look at all the impact craters that are formed on top of it. So when we plot up the diameters of those craters versus the area over which they occur, basically that correlates to an age. So a really old surface, you might imagine, would have a lot more craters on it because it's been exposed to space a lot longer than a young surface. So it's had time to collect a lot of craters. And the impactors that collided with that surface also tend to be larger over time. So earlier, there were a lot more larger impactors than there are now. So a really old surface has a lot larger craters and a lot more craters. And then we tied that to an age by using the Apollo samples that were brought back. So they were radiometrically dated to give a fairly precise age date for events that we think we understand in terms of where those rocks came from and where they formed on the moon. And so we have samples that we think come from specific impact craters like Tycho and some of the basins. And so basically we just took those ages and then compared it to the craters that had formed on those surfaces where we thought the rocks came from and plotted that up. And then that then basically fits the curve. The trouble with it is why there are such large error bars is that because the Apollo samples were collected from a fairly limited area on the lunar near side, and so we aren't quite sure if they are representative of a wide range of lunar history. So it's possible that most of them reflect a very narrow range of lunar history. And so the fit to the curve in that case wouldn't be very good because it would fit this one little narrow area, but not the whole thing. And so we're not quite sure what's happening in the really old times and not quite sure what's happening at the really young times because we don't have those samples. So one of the things that we actually do really need is a lunar sample from a young surface on the moon so we can help tie down that fit the curve. That's one thing that is on our list of to-dos, high priority to-dos. Oh, I think I lost your audio.
Oh, sorry. I had muted. It's an amazing process, and it's like about that question is that how old is something? The way that you're describing how it's determined is like, well, for one thing, thank God that we got some samples.
Yeah, so that's
otherwise it'd be really
at all practical.
Yeah.
There's so many uncertainties. Like we have to make assumptions about what the population of impactors has been over the last 4.5 billion years. So we make certain assumptions about what that population looks like, what the source is, what the sizes are, how it's changed over time. So that's one large area of uncertainty. And the other thing that's a little bit scary about the whole thing, actually, if you think about it too much, is that we use the lunar curve to tie down the chronology for the rest of the solar system too. So it's the basis for ages on Mars and ages elsewhere. So those uncertainties that we have in the lunar curve get propagated to other planets as well. And so that's why it's so important for us to make sure it's accurate.
Well, that's what you call scary.
I did say it was a little scary.
We are coming up on Halloween. I could think of a lot scarier things.
Yeah.
Well, it's interesting, Alan was talking about getting the audience involved, and I like doing that too. And just telling which crater hit first, I find is a really fun experiment to try on the audience. And I've gotten, kindergartners that can figure it out. And then, I'll show them like a picture I took on the beach of 2 footprints. And for the ones that didn't understand, it's like, well, yeah, you can really tell this. It's pretty, that part is pretty basic. Once you get layers upon layers deeper like you are, it gets a little bit more complex. But the basics of it is pretty easily understandable by the public.
Okay, well, you know what? We've gone about a bit over an hour, that's typical, and probably about ready to close off, and unless there's really urgent questions. I don't know, Josh, do you have anything? Did you want to unmute and ask something or say something? If not, then, gosh, Julie, thanks again. This has been really good. This is, I don't know if you'd say what, I bet you say that to all the speakers, but it's one of the best. This is really good, and thank you for doing it.
No, it's fantastic because I always tell audiences, the moon's volcanic and the Maria is, lava flows, but getting into this in a little bit more detail is very useful for me. And yeah, it's creates a whole nother level we can take things.
Yeah, yeah, it's great. Well, thanks for letting me speak. And if you have any questions, my email is on the internet, if nowhere else. But let me know if there's anything I can do. If you need some images, I can help you find them.
Okay, great. And I guess if people want to contact you, they can find out your contact information at the Lunar and Planetary Institute.
Yeah,
The
it's
website.
gonna be pretty easy to find. Just
Yeah.
click on my name and it should come up.
Okay. Well, thanks again. I'm going to stop the recording at this point and say farewell until the next Pacific Planetarium seminar, which will be in November.
Yeah,
Well,
Julie, are you just over at NASA Ames there?
I'm at LPI, which is next to Johnson Space Center.
Oh, okay. I was hoping you were more local.
No, couple
Okay.
time zones.
yeah.
Yeah. Okay.
Well, we're the Pacific region, but we get involvement from wider geographical area.
Yeah.
All right. Well, thank you so much.
Yeah, it's fun talking to you guys.
Okay. Thanks. Bye-bye.